All right, everyone, we are back and we are going to do problem set 2 solutions. So let's go ahead and read through this. What type of cell is present in each of these, A, B, and C? So we know this is simple cubic, this is FCC, this is BCC. All right. Number of atoms in each cell, 1, 4, 2. So let's just tick, tick. Number of nearest neighbors, 6, 12, 8. Tick. Number of nearest neighbor distance, all of those is going to be 2r. Lattice parameter, 2r here, 2r root 2 here. This is going to be 4r root 3. Tick. Next nearest neighbor distance, for simple cubic, it's going to be 2r root 2. For the other ones, it's this. Atomic packing factor, we know that this is our 0.74 and these are not 0.74. And I'm expecting you to calculate those, and you've seen those in our video as well. Are any of the cells close packed? Yes, FCC is close packed. Are any of these cells primitive unit cells? Yes, simple cubic. There you go. Number 1 is done. Now let me erase all these. Determine the crystallographic directions in A, or actually for C, excuse me, that's a typo, A. Determine the crystallographic directions. Are there any directions close packed in A? I'll make a note of that. So let's look at the directions and let's figure these out. So let's do this one first. So remember finish, which is going to be a half 1, 0 minus my start, which is going to be 1, 0, 1, which is going to lead to minus a half 1. I'm doing commas, I shouldn't do that. Minus a half 1 minus 1, and that will be multiplied by 2, so it'll be minus 1, 2, 2 half. There you go. That is this one done. So we got this. Let's do this one now. So let's go ahead, let's erase it. So here, our finish is at basically 1, 1 half 1, minus my start, which is at 0, 0, 1. So we're left with 1, 1 half, 0, which is going to be 2, 1, 0. Got it. This one's done too. Next one. Almost there. Let's go here. My finish is at 0, 1 half, 0. My start is at 0, 1, 1. So I'm left with 0, minus 1 half, and then I keep doing that, minus 1. So that's going to be leaving me with 0, 1, 2 hat. So got that. Done. And then finally, over here, we are going to be at finishes 1 half, 0, 0, minus 1, 1, 0, which is going to leave us with, we're going to have minus 1 half, minus 1 and 0, which is going to leave us with 1 bar, 2 bar, 0. There we go. We've got it. All right. Directions are always a pain, and they're not fun and exciting like all the other ones are. Let's get at this. Here we go. All right. Now, so we've got the directions. Are any directions close packed? No, because they're not. The only close packed directions are 1, 0, 0 for FC, for simple cubic. All right. For B and C, identify the crystallographic planes. So here, I'm going to have to reset the origin. I'm going to choose this as my new origin. My x-axis is new here, y here. So my x-intercept is 1, my y-intercept is minus 1, and this is a half. So it's going to be 1, 1 hat, and then 2 for this. What about here? Same thing. I'm going to set up my new origin here. Here's my new origin. Here's my new origin. Here's my new origin. What's my x-intercept? A half, which is going to be 2. My y-intercept is minus 1. And z-intercept, nothing. It's infinity. Bang. Be sure to indicate the origin select. Are any planes close packed? Nope. Indicate the close packed planes for A and C. A, there are no close packed planes. C, there are no close packed planes because we're not a close packed structure. All right. Calculate the planar density quantitatively for the plane in C. Ooh. Now that's a good problem. So we are going to go ahead and we can do this. So if I look at this plane, I have a plane that looks like this. I have two atoms here. And we can go ahead and we know that this is A. But this one's a little bit trickier. So we have basically a triangle that looks like this. It's going to be A and A over 2. So this is going to be X. Pythagorean theorem comes back to haunt us yet again. Not really haunt, but slightly annoy. And again, we're going to have to wait for Mathematica to pop on up. We can get moving here. So we can go through and we can go and say, for example, so I'm going to say solve x squared equals a squared plus a divided by 2 squared for x. And then shift enter. So it's, here we go. So we'll do root 5 over root 5a2 equals, so root 5a over 2. Let's just double check that that's correct. Probably should have just looked at that numerically. So those are the values, and my A for this cell is for BCC. So I don't see any other basically atoms intersecting this plane at this point. This is a little bit of a difficult one for like the true actual planar density, but we will ignore that for another another time. But the way that we want to calculate it, how many atoms? Well, this is going to be a fourth, so a half. So for planar density, we're going to have a half times pi times r squared. We're going to define our A, B, C, C equals 4 times r divided by square root of 3. And the area, so we're going to divide all this. Let's close this here. Divide all that, but divided by, we have A times A of BCC squared times square root of 5 divided by 2. And that is for sure not close packed. All right. Got it. Boom. Gone. Draw an FCC cell in D. So, face. Got it. Draw this direction. So, if I want to draw the -1, 0, 2 direction, I'm going to have to end up with, I know that this has to be, it's a finish minus my start. So I need this to be 1/2, and I need this to be 1. I need this to be 1, 1, and then I need this to be, as a possible answer, 0, 1. So that'll be my finish, that'll be my start. So 1/2, and then 1, and then 1, 1, 1. So here to here. So that would be one potential answer to this problem. So that would be my direction. Get out of here. Is this direction close packed? Yes. Oh, no, it's not. Of course not. Draw this plane. So it's a negative at the Z, so I'm going to pick mine. This is going to be my new origin here. So intercept x of 1, a y of a half, and then a z of minus here. So I'm going to go doot, doot, doot. There's my plane. Got it. Calculate the planar density of this plane quantitatively. Is it close packed? So it is not close packed because we know already it's not 1, 1, 1. So we can do something, again, very similar here. So let's go ahead. We have, actually we can set this up here. So this plane is only touching basically, so the number of atoms is going to be basically a 1/6 in this particular problem because we're not hitting the center and we're not touching that central atom at the top of that plane there. So now it's just really looking at effectively the distance, and we can look and see at what this distance is going to look like for each of the atoms. And basically we'd calculate that area here and we divide it by, so 6 atoms times pi r squared divided by the area of our triangle. And then we know that, again, we're using an A of FCC, which is going to be equal to 2r root 2. But it will not be close packed. All right. Which the directions within the empty unit cell below, or draw the following directions within the empty unit cell below, 212, 110, 232. They must be contained in the unit cell demonstrated in class. So let's go ahead. So 212 negative. And then 10, I'm just going to copy these so I know what we have to draw. Oops. 110. And then finally 2 3 2 3 2. Good. All right. Let's do, so how can I get, actually we'll do all of these first. Finish minus start, finish minus start, finish minus start, finish minus start. So I need this to be 1, this to be 0, I need this to be 0, this to be 1, and then this could be 1, 1. So these have to be 0, 1, 1/2, 0, and then 1, 0. And then if there's a third, I'm going to have to look at, let's go ahead and see. I need to multiply something by 3. I need to multiply something by 3 so I can get rid of the, let's see. So I have, if I multiply basically 1 by 3, so this will be like 0, 1 for sure. But now the question is, how can I get the, if I multiply something by 3, how can I get, or can I get just 2/3? Yeah, I'll just do 2/3. So I'll do here, I'm going to do minus, so it's going to be 1, actually 1/3 minus 1, so that's going to be negative 2/3. And then I'm going to do 1 and 1/3 here. There we go. So I think that should work. So 1, yep, that's good. All right, so I'm going to draw these. Remember, these are all my finishes. These are all my starts. So this start here will be here. This finish will be, what is it, 0, 1/2, 1. Yeah, 0, 1/2, 1. So this one, again, you could have different answers. This makes it a very difficult answer for me. This is my start, or actually that's a finish. 0, 1/2, 1. The start here is 0, 1, 1. So that could work there. And then my start here is 1, 1, 1/3. That's the start. And then there would be a third, 0, 1. So it would be like this. There you go. Draw these planes in the structure. So again, I see that negative here, so I'm going to start mine at the top. So this is my new coordinate system. So I know that the z-intercept is minus 1/2, my x-intercept is nothing, and then my y-intercept is 1/2. If I don't know how to complete this, I would just do my origin here as well. So it'd be, except I don't want to do it there. Instead, how can we, let's see, 0, 0, 2. Where else can we select this one? Excuse me. We could also select this here. So it'd be here, and then you can pick a point here. So you can go like this. So do people see that? Let's do that one more time. So I've got my cube as such. Boom, boom, boom. I can pick a point here because my y-intercept will be at 1/2. My z-intercept is at minus 1/2, and I'm going to connect those points. I can also start my origin here. My x-intercept, or my y-intercept is going to be here. This is going to be half here. Connect the points, and then bang, bang. So it's basically that plane that extends out there. If I'm doing 1, minus 3, 2, again, I'm going to have to go to the left. So I'm going to put my origin here because I'm going to have my intercept of 1. Oops. I'm going to have my intercept here, minus 3, which is going to be a third here, and then 2 will be a half, so it's just going to be bang, bang, bang. We got it. There we go. 6, 7. What type of material am I working with? What's the nearest neighbor distance? What is the next nearest neighbor distance? What is the element we were working with here? What is the integral in the first peak? Ooh, lots of questions. So we know it's a metal. So I am working with the type of material is a metal. My nearest neighbor distance is, this is equal to 2r, so that is my nearest neighbor distance. This is my next nearest neighbor distance, 3.26. But now we have to figure out what's the integral in the first peak. So we know that for simple cubic, so if I'm looking at my simple cubic BCC, FCC, my next nearest neighbor is 2r root 2 for both SCC, or simple cubic, and FCC. BCC is 4r over root 3. So we have to take, if I do ABCC, I'm going to just say AFCC equals 2 times r times square root of 2. I'm going to do BCC divided by 2 times r, actually 2r. And I'm going to do, look at that numerically, I'm going to do AFCC divided by 2r. So now I can look at that ratio that we have here, which is 3.26 divided by 2.82. That looks like it must be BCC. And we know that 2.82 divided by 2. So I'm looking for a metallic radii of 1.41, and it must be BCC. Where is my periodic table? I'm going to use a trick some student showed me, 1.41. Bang. Where are we at? Where are we at? Sorry, let me move some things around here. Where's 1.41? Where is it showing me? Let's go ahead and look at it ourselves. So, where are you? Come on, 1.41. There's got to be some more than 2. Anyways, let's look at our structures here. So we know from the symbols that if we are BCC, we have that basically hatch. And we know that this is our atomic radii here. So these aren't the structures we're looking for, or the droids. Don't see anything that would match. What's going on here? Let's look. Let's see. So we're looking for that 1.41, that's a hatch. I tell you what, molybdenum's pretty close. I would say that that's a good candidate that we have got there. So, but there's a better one. Tungsten by molybdenum. We've got a winner. I believe that that is tungsten. So, that is our solutions. So we'll see you all in the next video. Thanks. Bye.